All right. Hello, everyone. Welcome to the third meeting of the working group for the contribution of the MicroJIT to the OpenJ9 project on the 30th of July. So this is the third meeting of this series. So there were two items that I put on the agenda provisionally, which were to continue discussing integrations of the control logic and the code gen, as well as to see if there was any further discussion to be had on profiling. Before we start, does anybody else have any agenda items they'd like to add? Scott, is there anything in particular you'd like to add?
Not at this time. Most of what I wanted to talk about was control.
Okay. All right, well, let's start with that then. So, Scott, why don't you lead with the discussion with an update and your questions so that we can see if we can help you out.
Perfect. Thank you very much. So right now, what I've been working on for the past 2 weeks is moving to a GCR recompile setup. And I realized partway through implementing this that I would want to be able to test it, but I don't actually know how to turn GCR on. And as I was going through looking at how to enable GCR, I found a number of different options and flags that would tell the compiler not to use GCR. And so two kind of important questions cropped up from that. And the first one was, how can I tell the compiler that we need to use GCR? And the second was, is there anything that's going to prevent the compiler from compiling code if we make the first step in code compilation MicroJIT and MicroJIT's requiring GCR?
Okay. Well, I can take a stab at a couple of those. Erwin may want to chime in, or Philip, since they both have, or Daryl even, since they all have quite a bit of experience with the compiler. So the normal use case for GCR in the compiler is to deal with a situation where the compiler is getting overloaded with work, usually during startup or during a period of heavy class loading. So if the compiler detects that the compilation queue is growing faster than it can drain it, and that situation is sustained for a certain amount of time, the compiler is basically going to prioritize getting compiles done over the quality of the compiles to a certain extent. And so one of the ways that we can do that is that we compromise a little bit on the optimization, and we'll put GCR in, and the GCR will allow us to come back and compile the body again at the same optimization level a little bit later, basically once the counter is decremented to 0. And the counter decrementing can be controlled so that basically we may wait until we finish class load phase or something like that, so that we're basically not going to just have stuff jumping immediately back onto the queue. So a lot of the control heuristics that you're seeing are around that kind of notion. Now, there have been in the past code gens that haven't supported GCR, and so then GCR isn't an option. And on some platforms, it didn't make sense from a performance perspective. So again, it was turned off. I think Zed was in that position for a little while. But whether you want to use GCR or not is really just a function of the compile you are doing. And so if you put the counter logic into the body and you ensure that the counter is initialized and the control logic is there, there's no reason that it won't work, right? Because the functional reason of needing to support it, well, you're supporting it, right? You would be generating the code paths that are needed for it. So from that perspective, I don't think you have to worry so much about all of the details. You would just have to make sure that the method body is marked correctly. So Erwin, did you want to add something to that?
There might be some subtleties in the control logic, because like you said, the GCR is sort of it's, you compile it at, say, warm, and then you recompile it at warm again. In this case, I haven't been there for the other two. Is the what is the invocation count going to look like on a method, right? Like, is the MicroJIT is it essentially gonna be almost like, will the method be considered it has been compiled if it's been MicroJIT?
I believe so, because the pointer to the body will be installed in the J9 method, right, Scott?
Yeah. So the initial reason to switch to GCR was so that we could use a separate count for MicroJIT and TR, and we would simply pass in whatever TR's count was minus MicroJIT's count to where we initialize the count for GCR, and then we would use MicroJIT's count instead of TR's count in the extra field, and the first compile would be a MicroJIT compile if that was available.
Right. So then that would just mean that in the control logic, when we trigger a GCR, we would have to check if the body was a MicroJIT body, and if so, then the optimization level would default to warm or whatever it is, right? Rather than recompiling at MicroJIT opt or whatever we're going to call the MicroJIT level.
Yeah, exactly. We're gonna have to have just a few checks here and there.
Yeah. But most of the control logic, most of the logic that would gate whether we're going to generate it or not is not going to be relevant, right, in this situation, because a lot of that's just in the compilation setup for main TR, which isn't relevant for MicroJIT, I don't think.
Yeah, like, I think, given that, I guess it would be whatever logic we use to decide to do a MicroJIT body, like to set up the comp object and everything like that. That would have set up DCR. So when we're getting a recomp, we would sort of get the body info and then say, I think there's a flag on the body info or something that says, oh, this is a GCR method, and the reason for recompile, the entry, the method to be compiled entry would, I think, have like a thing that said, oh, this is a GCR body, because when we print out the line in the vlog, we know that the method was recompiled because of GCR.
Yeah.
So I believe, yeah, you're right. Like, it would just be like, there would be nothing else we would have to do, because at this point it would just be a recompile.
Yeah.
Okay, so that was part of the control. The other was that I noticed something in the magic word. The magic word field had something related to what kind of recompilation setup was being used. Is there an easy way to check for all the things that are going to touch the magic word and check to see if it's using GCR, so that I can make sure that nothing is going to accidentally treat something as TR when it's MicroJIT?
When you say magic word, where is this?
It's the 32 bits immediately before the interpreter's entry point into a JITted method. I
see.
In the pre-prologue. Yeah.
It's also magic, Erwin.
I noticed in a couple of places it was called the magic word, so I thought that was the name.
Yeah, I don't know why. It's like, I mean, it's the linkage info, and I've seen those comments though.
I think part of it's linkage, and the other part of it is the offset to the JIT to JIT start address. So I guess that's why it has a different name when it's together.
Yeah.
I believe we also need the offset to the persistent metadata. Or sorry, I guess it wouldn't be the offset. I think we encode the metadata pointer as well.
Yeah, I think that's right before. It's the metadata pointer, and then after that, the word is the bits and the offset to the the offset to the JIT entry point.
I assume the metadata will tell us whether it's a GCR compile.
So when you mentioned the metadata, when I was going through it around, I want to say it was sometime in September or October last year, what I saw right before the magic word was something called a body info. And I know that there's something else called a metadata. So has that changed since then? Is that no longer the body info?
I don't think so. I think there's just a pointer to the J9 exception.
Okay.
Is that true? I don't know. I think it might be the body info. Because I don't think the metadata.
Or it could be the body info, and then from you get the exception.
Yeah,
Okay.
or I don't know if the body info even has a pointer to the metadata. I think you'll like everywhere I've seen, you have to look it up from the ABL trees.
There was, hold on, I can pull this up in front of me really quick here, because I have been looking at this somewhat recently. If I remember correctly, there's something on the compilation object that is set, where you set the metadata associated with the object. And before I did that, nothing ran. It was one of the steps I needed to do to get MicroJIT working the first time around.
I doubt it's the metadata because that's created at the very end of the compile. Where the body info is created.
Crashing. Yeah, something was crashing when I didn't have set metadata called. So set metadata on, I guess that's the compilation thread. So the compilation info per thread base. Now the body info, I was allocating that during the pre-prologue generation. Is there already a body info created that I should be linking instead?
I thought when we create the recompilation info, the body info gets created as part of that.
So let's see. What I am currently linking in my pre-prologue, I create a field for a pointer to the body info, which is a persistent JITted body info. Then in the prologue, I pass the location to that pointer in, allocate it, and set it up, and then I pass that body info along later when it's used to do something. Right.
I think it's already created.
Okay, so it's already created. So there's a so that's incorrect. That's a bug that needs to be fixed. I'll really quick here.
In terms of figuring out whether it's GCR, let me see.
Would it be the reason for would it be the reason for recompile, Erwin? There would be a reason for recompile when we trigger it, right?
Yeah, I'm trying to see. Apparently, it's body info, which gets the method info, which then gets the reason for recompile. So, but that said, the body info should still be able to tell you whether it's a GCR body or not, because it describes the body, right?
So I should be able, or I should have to take the find GCR already generated, and then put
yes, the body info has
GCR.
Yeah.
The body info has the flag.
Encodes the TR _ persistent JITted body info as get uses GCR. I'll put a link in the comments at least where it does it.
Thank you. Okay, so I think that covers most of my current questions on control, and that probably saved me a bit of time trying to figure out that body info thing. So what I've managed to do right now, I've got, because we're not going through the standard TR code gen and so on and so forth, I wanted to, or I needed to be able to patch the caller if we're going to be able to support patching MicroJITted code, which if we're putting it all on the same field is going to be a requirement in the glue code anyway. So I'm hoping that what I have done to do that is correct. But the way I'm currently doing that is I'm just making the assumption that the return address from where I have been called, or whoever called this method in my trampoline, is going to be on the stack in at the top of the stack, and I'm using that to find their call instruction, and then I'm patching it directly. The way it's done in the x86, what's that called? x86 unresolves.nasm for the 32-bit case. Is that going to be fine, or am I going to run into some problems there?
Can you just ask that question one more time? Sorry, I didn't quite get the whole thing.
Okay, so in the x86 unresolves.nasm, the glue code for a static call subroutine is patching the caller. And in the 32-bit case, it does it inline in the assembly, just grabbing the stack pointer off of ESP. But in the 64-bit assembly, it calls a C helper with JIT call C function. It's MCC call point patching on wrapper. So my question was basically, is on the code gen side where I'm creating a trampoline over the old MicroJIT code when someone eventually recompiles this. When I generate that, I'm trying to create a trampoline that will also patch the caller so that they will directly call the recompiled JITted method. And the way I was doing that was trying to do essentially the same thing that 32-bit code from x86 unresolves NASM does. It just grabs the return address off the stack, and then it uses some knowledge about like how big the call instruction is, and simply walks back the number of bytes to the start of where the address to call is, and then I'm catching the JIT to JIT call and grabbing that return address off the stack and patching it with the new JIT start address as part of that trampoline. So my question is essentially, is that going to cause a ton of problems? And is there some standard path that I can conform to go down that route by following, say, the MCC call point patching on wrapper? Or is that going to cause a ton of problems because it's making assumptions about the structure of code and the existence of IL trees?
Well, so are you using? You must be using trampolines as well on in the MicroJIT.
Well, this is the first trampoline I've written for MicroJIT.
Okay, I mean, I think the reason that call is made to the call point patching is because it does the work to figure out whether or not you need a trampoline at this site, and then if you do, it goes and either creates one or looks it up, that kind of thing, and then uses that address to patch in the code. So that kind of logic is a bit more difficult to write in assembly. So that's, I think, why it was written in C. So I would imagine that you're going to need some kind of logic like that. So, so sorry, it's a bit hard for me to visualize this without actually seeing some code. Do you actually have code that you've written for this?
So I have some AMD 64 code, or code written for AMD 64. It's on the C side, and it's using some templates. I can pull some of those things together here and then share screen.
Sure.
Just very quickly, I'm operating in a virtual machine on my workstation here, so I'm going to have to see if I can get this correctly set up. Okay. So that is the virtual machine connection. So are you seeing C++ code on your screen here now?
I'm seeing Visual Studio Code at the moment.
All right, perfect.
Sorry,
That's what you should be seeing.
sorry.
All right, so this is what I've written so far for creating a trampoline and patching it as a static thing to just the code generator class, not to a specific code generator object. So because MicroJIT doesn't really use insights into the method for a lot of things, it would probably end up working the same way. If I know the old JIT start address, I can figure out the old JIT to JIT start address using this magic word trick here.
So who calls trampoline patch?
Nobody yet. I'm trying to set this up for GCR. The idea would be that when you go to recompile, that we would have to modify where the GCR is to identify that the code is MicroJIT, and then correctly patch this after the recompilation.
So this would be called somewhere on the, so in the body that you have GCR, and it figures out, oh, a recompile is necessary here. It is in that body that you would eventually end up calling trampoline patch.
Yeah, so I didn't know the exact location of where this would need to go. I imagined at the time that I made it, since I made it in C-land, that I'd be doing this somewhere around, if I can pull up the, it's not the bytecodes, it's in the linkage that I made this. So I just need to scroll over until I find the linkage. So here, where we eventually have to call where we eventually have to call the, oh wait, no, that's the wrong area. Hold on, I'm getting turned around here. I apologize. So when we generate the GCR block here, we eventually have to call this JIT retranslate caller with preparation method, which is one of the other things I'm working on at this moment, is trying to figure out where that is. But I've got it narrowed down to 2 places. So
it's in CodeRT
go here.
Sorry.
Sorry. Okay. So I just thought it would probably be called here, but I would like that's more like where I thought it would go, not necessarily where I know it would go. So there's definitely the possibility that something, since this is just a static method, we could call it here after setting the body before going to the original first block, because then that would also patch the original first block and cause it to patch the caller, and then patching the caller before jumping to the newly JITted method on the new JIT to JIT start address.
So original first block is in the new body?
Original first block is in the old body, but the patch will patch over original first block. So original first block would then just jump to the new body.
Okay.
But I'm also completely unfamiliar with how GCR works in practice. I only understand it at a high level. So any one of those things could be in the specifics of how it operates, and the nuances could mean drastic changes in where this should be.
Okay, it's been a very long time since I've looked at this code, so I don't really know it in depth, but I could certainly figure it out, so I can reason through it with you.
So
Yeah.
one of the things with recomp is that how you, like, I believe, and I could be wrong on this, but the GCR is sort of used to trigger the recompile. But once the new body is available, my understanding was that we just sort of have a helper call in the pre-prologue, and then we just patch the start PC of the method to just jump to the helper call, which does the work of patching over the caller to call the new body. So I think the logic that does that is independent of GCR. I could be wrong though.
Okay, because when I asked, I forget who I asked about this, but when I asked someone about this, I was told that I would have to make the trampoline and make code to write the trampoline in MicroJIT so that it would be able to do that.
Yeah, I believe that. I think you'd have to add the helper that does that. I don't, or maybe you just have to make sure that you call the same helper. Like it all.
I think you're right, Erwin. The thing that you might have to be careful about is that a lot of that code is very sensitive to the shape of the shape of the method and the size of the prologue and the pre-prologue and whether or not there's a counting pre-prologue or that kind of stuff. So a lot of those offsets are really fixed. So and even the collar shape as well. So you have to make sure that if you're going to use that same logic, that the MicroJIT code and in the prologue area needs to look pretty much identical to the way that it is in the non-MicroJIT world for it to just work. Otherwise, you're going to have to adapt in some way.
Yeah, that makes sense. I guess I'm curious as to whether given the GCR framework here being used is more or less the same as in the other case. I don't know if it makes sense to add logic into the GCR generation stuff to do the patching, or we should just follow the same paradigm as the other parts of the code, and maybe for MicroJIT you have to write a new helper. I don't know what's better.
Okay. So do you know offhand what that helper thing is called that does the patch, or is that just part of this retranslate with preparation?
No, I think JIT retranslate preparation requests the recompilation. The actual helper call that patches the caller of the method, I'd have to take a look at the code and see where we do that in compilation thread.cpp, because I'm pretty sure we have to patch the old body. I'm not sure exactly. It might be in recomp.cpp where there's a bunch of like fix up start PC methods. And then you'll see what Daryl was talking about, where there's a bunch of like hard-coded offsets that require the shape to be a certain way.
Yeah. So I've actually had to go through this code recently because I'm doing a little bit of work right now on the recompilation in the full JIT. So I have figured out some of the stuff, and I can share some of that with you. Unfortunately, I have to drop right now because I have to jump onto another call. But I can sync up with you a little bit later, and we can, if you haven't got anything resolved on this call, we can hopefully work through something.
Okay. I may have to delay that to tomorrow.
Yeah, that's
a better day for you.
Sure, or perhaps even early next week because we're off tomorrow through Monday.
Oh, right. You guys are off Friday. I forgot. Monday's a holiday here, so Tuesday?
Sure, sounds good.
All right. We can hook up afterwards there.
Okay, all right, thanks.
Thanks for coming, Daryl.
Yeah.
All right, so on the, I guess back to the body, I quickly need to, oh no, I already made that note. All right, I guess I can stop sharing this here now. So that's where we are right now today on MicroJIT, is trying to hook up GCR, and the next step after that is to remove the old extra 2 field. I'm hoping before September to have this working with GCR, doing full recompilations. Hopefully somewhere by mid-August is the hope. So what I've gotten from this today is that we need to get the body info that's already generated before the call to MicroJIT's code generation. And I need to look further into how recompilation happens with Daryl, and that the patching of the caller probably doesn't need to be done inside the trampoline patch. Would that all be correct?
Yeah, I think that covers it.
All right.
Daryl has the most experience on that actual intricate patching sequence at the moment because he's been in there. So, unfortunately, it's one of those areas that's very complicated, and you only really know it when you've been working on it, and it doesn't get touched super often. I think the best bet for you to get some reliable answers is to go through it with Daryl, and hopefully that'll get you on the right path to getting it fixed up pretty quickly.
Yes, thank you. And I know Daryl's gone, but thank you everybody who comes to these MicroJIT calls and helps out with this. This is incredibly useful. So on the code gen side of things, it's not in the public PR, but we're because the public PR was about getting a compilable method that's runnable pushed up. But internally right now we're up to 120 supported bytecodes. And the big things that need to be or are left to be supported are doubles, invoke virtual, get and put field, and support for arrays.
You must also be needing to do support for invoke dynamic and like constant dynamic and that stuff, right?
So invoke dynamic we put a big pin in that because I knew that invoke dynamic was an incredibly complicated bytecode to work on, and the expectation, at least from Ken and Marius, was that invoke dynamic was probably going to take someone's entire master's thesis to complete, just because of all the various intricacies and complexities in the bytecode itself, and how we would handle generating assembly code in a template that would always execute the same way to somehow correctly invoke dynamic without falling back to the interpreter, which is the whole reason we had to rewrite MicroJIT from the ground up at the start, because the MicroJIT, as it was when it was last touched in 2016, was relying on the fact that it could jump into the interpreter, let the interpreter handle something, and then the interpreter could jump back into the MicroJITted code, which I have been told by Marius, Daryl, and Graham Chapman is no longer an option.
Mm-hmm.
So we're currently putting a pin in invoke dynamic. The objective here is to eventually have support for all 205 bytecodes that are in Java 8, and then add in any additional bytecodes that have come in since then. Be able to support Project Valhalla, but until we have full support for everything in MicroJIT, it will probably remain something that needs to be turned on and is more or less an experimental feature. Until we get that full support. But as you can probably tell by the statement that it will be a student's master's thesis to probably do invoke dynamic, we're intending to keep working on this.
Okay. Yeah, I was only, it's just because you didn't mention it, and it is such a large thing, as you say, but it's also exceedingly prevalent in any version of Java after 8, right? Even if you bring the system up enough to do Java minus version, you're going to run several thousand invoke dynamics in Java 14. Just, that basic level requires, it's become pervasive in the JCL in the newer versions.
Okay, so I was under the impression that invoke dynamic was more to allow dynamic languages to run on the JVM. I didn't realize that Java compilers were starting to omit invoke dynamic as part of running Java.
Yeah, so invoke dynamic was used in Java 8 to implement lambdas. So inline anonymous functions in Java 8 are implemented using invoke dynamic by Java C. And in newer versions, invoke dynamic is being used to implement string concatenation. So in Java 8, if you do string plus something plus something plus something, to make a string, you would get a new string builder followed by a series of append calls followed by a toString. Whereas in the newer versions of Java, you'll get a invoke dynamic to a method handle chain that will construct the string, and doing that a lot is more efficient than the string builder approach. So in the newer versions of Java, the use of invoke dynamic is becoming quite common, and there's increasing use of it by the language. So there's for the MicroJIT to be able to run anything newer than Java 8 with any success, you will almost certainly need to support it.
Okay. All right. I thought I thought the lambdas were being done like through a trick where GCC was creating anonymous classes. I didn't realize they were using invoke dynamic at the the Java C level to do that.
Yeah, so Java C generates uses a thing called the Lambda metafactory. So the invoke dynamic bootstrap method uses the Lambda metafactory to build the anonymous method, and it's installed as the target of the invoke dynamic, and that becomes the implementation of the method. So yeah, if you write a Lambda, you'll get an indie in your bytecode by default. And as I said, there's been changes in the newer versions of Java C after 8, so 11, 13, 14, and 15, that are using invoke dynamic in more cases for performance reasons or for adaptability reasons, so that they can do more things with the language. So it's become a tool that the language designers and the library implementers have been turning to do things. So just so you're aware, it's not a weird and exotic thing that you're only going to see if you're running JRuby, for example. It's something that you will see in plain, ordinary Java code generated by Java C, when you're working with these newer versions.
All right. So that's going to be a little more important than previously thought, and I may need to have a chat with Ken and Marius to see if the next master student we get on the project maybe starts looking at invoke dynamic once this is in.
Mm-hmm.
So the way we've been doing invoke static, that I imagine we're going to be doing invoke special, since it uses the same glue code in the unresolved NASMs section, is that we've been essentially only looking at things that are resolvable at compile time, and we've resolved the static method and then patch in the address. For invoke virtual, I recognize that has to go through a table. So how do you actually set up that table? Is there an example of where some of that code is on TR side? Or is it probably, for my purposes, since I'm trying to write assembly anyway, is that going to be easier to just write some, generate the log file from TR and see what comes out?
Well, so the vtable exists at negative offsets from the class pointer, right? So the it's from the class pointer. So if you have an object and you're going to do a virtual dispatch, you have to obtain the class pointer, which is the first either 4 or 8 bytes of the header, depending on your whether you're running compressed refs or not, 32 or 64 or not. Mask out the control flags or the flag bits, and you then have a pointer to the J9 class. Forward offsets from that J9 class are the layout of the J9 class data structure itself. And then negative offsets from that are the vtable slots for that particular class. So those will contain pointers to the J9 method that are going to contain the pointers to do the dispatch. So the J9 methods are installed in there. So you can have a look at the lookup that's done in the TR code gen to do that, but it essentially ends up being an indirect. You have to indirect off the class pointer to get the destination, and then you can try and do the dispatch, whether it's going to be through the VM or not.
Okay, and I'm willing to bet there's some glue code similar to the static and special glue code that will do an automatic patching that'll pull in the invoke virtual and do the JIT to JIT call. Is that, or no? Because
for an unresolved, or we're talking unresolved or resolved?
Yeah, I just realized. So for unresolved, that would probably be not patchable directly. It wouldn't go through glue code. It would have to dispatch to something else. And I'm imagining also that given that methods that we're calling invoke virtual on could be for objects that have been passed in, there's probably no JIT to JIT patching there without polymorphic inline caches. And
correct. So you have to, so you have to dispatch through the VM.
Okay, and we probably won't be, at least in the early phases, doing any polymorphic inline caching.
Yeah.
And given that this is templated from the get-go, I don't see how we would be doing polymorphic inline caches at all, because that sounds like something that's going to require profiling, and at that point, it's going to be done in TR anyway.
Well, it depends whether it's a statically, so you could have statically profiled targets, right? So a polymorphic, the layout of a polymorphic inline cache for a virtual dispatch would have some number of what we call static pick slots, which would be slots that compare for a particular destination type or method, depending on the test that method. And then you're going to pre-populate those, some number of those with whatever the profile data has given you. And then we would have a sequence of slots that would be self-populating. So when you come into that slot, it would call down to a helper to populate the slot, which would then turn it into a compare followed by a jump, followed by the call to the target. And so the layout is fixed, but populates itself at runtime. With the most frequent, like the first thing that gets there fills the first slot. Second thing that gets there, if it's not the thing in the first slot, fills the second slot, and so on until the slots are filled, in the hope that the most frequent things are the first things that arrive.
Okay. So it's because it's not using profiling information in that case that you described, it could be doable on the templated compiler. So that is an optimization probably worthy of a paper.
So there's doing it with the self-populating, and then even unless you're running it like count 1 or count 2 or whatever, I mean, if you're at 10 or whatever, there may be enough profiling data to suggest that one or more static picks would be worthwhile.
So I can tell you that that what we're doing with MicroJIT now is using even less sophisticated profiling, even less sophisticated optimizations than the previous MicroJIT. And the previous MicroJIT was managing to see a decrease in runtimes on the decapo benchmarks after going to counts that were above 20. So 20 was kind of like the hotspot of like when we wanted to hit it. Early 20 was not enough runs and was compiling stuff that wouldn't get run again. And after 20, we were just waiting too long to compile things. So given that our compiles should be even faster now, I'm imagining that our counts would be somewhere in the vicinity of 10 and 10 to 20. And one of the things I wanted to attempt was trying to get compile times fast enough that we could see benefits for counts of less than 10 and even check to see if there were applications that were faster with counts of 0.
Right. So I guess all I'm saying, though, is that if you have any profiling data, it may still, like, I'm not saying you have to do it as part of the first cut, but there may still be enough benefit from avoiding the indirect dispatch through the VM to lay down one or two static picks with whatever the one or two most frequently seen things are based on whatever minimal profiling is available at that point, right?
Yeah.
Because the indirect dispatch is exceedingly expensive, right? You have to go through the VM, so you're pinging off into another DLL and losing all your locality and everything. So.
Oh yeah. Okay. There's no way that code is gonna be anywhere close.
Yeah.
Yeah.
So, but as you say, it's an optimization.
Yeah.
So we don't need to address that now. Okay.
Yeah.
All right.
Yeah.
Go ahead.
I was gonna say I was mostly just wondering when I started this, like what kind of things needed to be looked at for Invoke Virtual, and Invoke Interface, I imagine, is similar to Invoke Virtual in that regard, and that there's something looked up into.
Yeah. The interface dispatch, like looking up an interface target, is a little bit more complicated because there's a linked list of I tables that are hung off of the J9 class. So you have to walk the I table. To find a particular entry, you have to walk the I table list. I think most of that's generally done by the interpreter. We normally just ping off to them and let them do it if you're going to do it, because it's going to be expensive. There's no real benefit to doing it inline.
Okay. All right, so I guess the Invoke interface might actually be easier than the Invoke Virtual, but if I am pinging to the interpreter as a steps on Invoke Virtual, they may end up being very similar.
Yeah, they'll look fairly similar, I think.
So I guess that's all the questions I had on CodeGen at the moment, because mostly the other questions I had at the start on CodeGen were part of setting up GCR, which is really control.
Right.
So you mentioned the iProfiler and the JIT profiler, and spoke previously about how the current JIT profiler works, JProfile, and how it uses control flow graphs.
Yep.
We have a much more direct relationship from of bytecode to block of generated code than TR. Would it possibly make more sense to hook up to the iProfiler instead of the JProfiler? Well,
so iProfiling is profiling that's gathered by the interpreter as it executes bytecodes. That profiling is always on. It populates its data into buffers that are parsed periodically by the sampling thread in the JIT, and that data is stashed and then used when compilations are run. The iProfiling data is only generated by the interpreter. And that mechanism is not exceedingly lightweight. The records that you have to generate to go into the iProfiling buffer are quite complex, so they're not going to be fast to build. The JProfiling implementation that we have in the JIT is significantly more lightweight. The layout, rather than putting events in a buffer, it allocates structures for the method and then counters for path frequency directly increment locations in memory. And value profiling uses a special form of lightweight special hash table that you'll have seen in the report. So from a performance point of view, if you want your code to run fast, JProfiling is definitely the way to go, and would allow you to profile some things that the interpreter doesn't profile at the moment.
Okay.
And if you have the notion of blocks of code, the building the control flow graph from that would not be supremely difficult, and that would then let you at least place the path execution frequency counters, and the value profiling could be done more selectively depending on basically wanting to profile virtual dispatch targets and type tests. So
the way we're currently doing, like the closest thing we have to blocks of code right now as a conceptual entity in the MicroJIT code gen is a table that we use for storing targets and for jumps. So we have, by the time we get to the end of compilation, we have a table of all the instructions that will be the target of a jump instruction. And we also have a table there, or would be able to easily create a table of jump instructions. So we would have source and destination for all the possible jump instructions that we've generated. That's the closest thing we have to the concept of like basic blocks or a control flow graph.
Right.
Right. That was why, and I very early on you kind of alluded to the idea that it definitely wouldn't work. Because I was imagining the iProfiler would also have some concept of just data structures that I could create templates of, copy them, and then fill them out and send them. But it sounds like there's much more there with the concept of records and queues. So that's automatically right out. There's no way that we could do that in JITted code.
Yeah, I mean, the simplest thing that you can do, right, is essentially like you, at the very least, you're going to have to do a scan through the instructions of the bytecodes, most probably, to know where the block boundaries would be, right? Because you're going to need to leave space to insert the profiling counter, right? The simplest thing is you just count every block, right? That's the simplest thing. You just go and spray a counter in every block. Now, the overhead from that will be quite high because you'll be updating a lot of counters in memory, and those counters will be near each other. And if you end up with the method running on multiple threads, you can end up with the processors thrashing each other trying to write the cache, right? Like thread number one
generate a ton of invalidates.
Exactly, and then everything just goes to hell, right? So the point of the J profiling for block frequencies is to place the counters using whatever profile information you have available to try and keep them off the hot path, right? And it tends to prefer placing counters at points of maximum fan out as opposed to maximum fan in, right? So if you have a choke point that all of the paths go through, the algorithm tends to avoid those points because it prefers the higher fan out where the frequencies are lower. And the benefit of that is that in those fan out areas, unless they're highly biased, multiple threads executing the method are going to take multiple different paths, and you get less invalidation of the caches doing that, especially since it will also try to, well, it will be the way the algorithm works, it will play for an acyclic region, it will place one counter on the hottest path, and you'll encounter two counters on the second hottest path, and so on, right? And once it has cycles, then it's sort of one on the hottest path of on the hottest path of the innermost loop, and so on, right? So it does a very good job of keeping the overhead of the counting low. The cost is that you do need a notion of the control flow graph of some kind, because you're going to need to process that to pick the places where you're going to put the counters. Now, there is a place in the TR compiler where we process the bytecode to produce a CFG. We produce control flow graph nodes and blocks with TR nodes that are just the start and end. You wouldn't have to do all of that. You could create a different kind of CFG node that's compatible with the type that's expected by the algorithm. But essentially, we do that just by doing a pass over the bytecode, right, and looking at where the branches are targeting. We do that during code size estimation in the inliner. So there's in ECS, there's a place where we build a fake call graph, a control flow graph, sorry, that would suffice for things like doing deciding which places are going to have counters inserted, right? So you'll have to think about whether the cost is worth it. But my experience with writing the J profiling is that the counters can be very, very expensive, and that a small use of compile time to significantly reduce the number of counters can be very worthwhile. Now, maybe you don't go quite as optimal as what's in the current J profiling, but eliminating counters from the hot path will make the profiling significantly more tractable. So, things to think about.
Okay, so it sounds like J profile definitely the way to go. That I'm probably going to have to add some more infrastructure to our metadata pass that goes over, because we do a 2-pass thing where we pass over the bytecodes once, collect all the information we need about which bytecodes are where, and then in the second pass we just generate a template for every bytecode. And
right.
we need that first pass in order to know how much space right now to allocate for the local table,
right.
for all the local variables, because we store a local table on the stack, and then every load and store instruction, every load and store bytecode grabs a value or puts a value in that table.
Right.
Where we do no fancy optimizations or insights into whether something's already in a register or not from being a parameter or not.
Mm-hmm.
So I'm imagining in that same pass where we figure out the size of the local table and how many slots are needed for each argument, that we can also put in all the other things we need for creating a control flow graph and create a control flow graph for the method. We'll probably need our own node in that class hierarchy for MicroJIT code, but if there is one that kind of encapsulates the idea of a block with a single entry point at the top and multiple exit points at the bottom, then I can just build a control flow graph out of that. And
well, there is already a CFG node and there is a TR block, so you can have a look and see what those look like. If they're too big for what you need, then yeah, something equivalent to a CFG node is what you would need.
Okay.
And there's a CFG edge, which is used for the connection, which is basically just a structure with a pointer. And then the successor, the predecessors and successors are lists of pointers to the next and previous blocks.
So that's sounds like that by the description you just gave me by saying there was a list there. That sounds like the edge encapsulates the idea of multiple entry and multiple exit.
No, sorry. So the CFG node has lists of predecessors and successors, which are edges, which themselves have source and sink pointers.
Okay, so I got confused there. I thought the lists were in the edge for a second.
No, the lists are in the node. The lists are in the nodes.
All right. So I may look at delegating that profiling to the other PhD student on the project. When she's done with her current task right now, she's working on getting doubles working. Which is the last math instructions we have left are the doubles. We've got floats and all the other things working and tested.
Right.
So that would be good there. Because if we could get both of those things, if we could get both the recompilation and extra 2-field, so that we don't have an extra 2-field anymore and we recompile through GCR, and we get that profiling working, that would be amazing for getting the first PRs in. And then we can move on to grouping some of this bytecode work we've done into smaller PRs that just add support for methods.
Right. Yeah, sounds good.
All right. So I guess that's it for profiling. I don't know if anyone else has any other business, but I've definitely carved out a ton of stuff for me to do for the next 2 weeks.
Yep. Well, the Militant Front for the Prevention of Boredom has struck once again. It's a very militant organization. Okay. I think we'll probably wrap it up there. We're on the 1 hour mark. So I'll let you liaise with Daryl. Hopefully you can also have a look at the linkage and just trying to not duplicate too much of the linkage. So Daryl would probably be a good person to talk to about that as well. Yeah, we can. I guess we'll meet again in 2 weeks, right? So it'll be the 13th of August at the same time we met today. If that's good for you?
I believe that's good for me. I am going to quickly double check. I believe the final exam for my course that day is in the morning at 9 a.m. So I believe there's no conflict there.
Okay.
I'll just do a very quick double check. This is the course page, content page, overview, midterm. Final is on August 13th at 9 a.m. Yeah.
Perfect. And you can load yourself up with more work to do in the afternoon. What a good way to celebrate.
A great way to celebrate.
Okay, well, thank you everyone for that. I will try and get this recording posted to OpenJ9's YouTube channel as soon as I can. So thank you for everyone for attending, and we will convene again in 2 weeks. Until then, bye-bye.
Thanks for coming, everyone.